Welcome to Lesson 4 of the Biochemistry Literacy for Kids Instructor Training video series. This is a really cool lesson because in this lesson we start to learn the origins of molecular bonding. Why do atoms bond with each other? Can we get a more technical chemistry explanation for that other than that 4-3-2-1-0 rule? So we're going to learn the origin of that rule in this class. The first thing that you know about how electrons arrange and how atoms are built is from this rule number 1 that we learned previously, that electrons like to spread out into their orbital if there's room. However, when they run out of room in the orbital, they're forced to pair up. And we see that happening in fluorine, where there's too many electrons in that orbital, so we see a lot of pairs. Something like a nitrogen, there's fewer electrons in the outer orbital, so they can spread out. We don't have to pair up electrons unnecessarily because there's plenty of room in that orbital. So you're getting kind of a sense of what we mean by this. Now, the second thing about electrons that you're going to learn in this lesson is that lone electrons in a certain atom like to pair up with lone electrons from other atoms. So electrons like to have a buddy, but that buddy has to come from other atoms. That's going to be the thing that we're going to practice a lot in this lesson, and that's the origin of molecular bonding. So what I have for you is a little funny analogy here. If we're saying that lone electrons like to get a buddy, it kind of means that they like to dream about certain electron configurations. So for example, hydrogen has one lone electron in its outer orbital, and therefore it wants a buddy, so it dreams of having a helium configuration. It doesn't dream of becoming helium because it can't become helium. Why? Why can't hydrogen become helium? Because hydrogen isn't helium. It has one proton. Helium has two protons. So we're not actually becoming another atom, but we're getting the configuration of one of these noble gas atoms. So you're going to see these little dream bubbles a lot in this lesson. Hydrogen dreams of the electron configuration of helium. It wants another electron for its outer orbital. What about carbon? Carbon dreams to be neon. It would like to add 4 electrons to its outer orbital to assume a neon electron configuration, a noble gas configuration. Same thing for hydrogen. Hydrogen would like 3 more electrons. Oxygen would like 2 more. Fluorine would like 1 more electron. They all dream of having the neon configuration. Let's now check out some animations to visualize this process. We know that hydrogen dreams to be a helium configuration. It has 1 lone electron, right? The black box is the indication of which noble gas the certain element would like to be like, or which one it would like to dream of. What if we have another hydrogen atom nearby? That also has a lone electron that would also like to be a part of a helium configuration. How does it work in chemistry? We get a pairing up of those 2 lonely electrons, right? If the 2 electrons dream of having a buddy, why not buddy with themselves? This satisfies that desire to be in the helium configuration. So how do we represent that pairing of electrons? That pairing of electrons is represented by a bond. We can say this another way. What is a bond? A bond is a shared pair of electrons. If we kind of look at that again, we have 2 atoms that are joined together. In your model set, those 2 atoms are represented by the white spheres that you use for hydrogen. But what's the gray bond? The gray bond means something very specific. It doesn't just mean connection of 2 atoms. It means a shared pair of electrons. So we can see how those 2 electrons are right over the bond, and the bond is a shared pair of electrons. So a kind of mantra that I ask my students a lot, I say, what is a shared pair of electrons? What is a bond? And their job is to repeat back, that is a shared pair of electrons. It means something very special. We can draw the molecule out in the way that we're familiar. That bond now has a greater significance for us because we know that bond means 2 electrons. Let's go on to the next element. We're going to skip ahead to boron. We're not going to do helium because helium can't make bonds. And we're going to skip lithium and beryllium for now because these actually form more ionic compounds, which comes in a much later lesson. We're going to skip over to boron for now. Boron we know how to build. It's the 4th element on its row. Sorry, it's the 3rd element on its row. So we know that it has 4 unpaired electrons because there's plenty of room in that orbital. If we just stick with the hydrogens, we can kind of realize that because there's 3 unpaired electrons, we can readily create 3 bonds with 3 hydrogens if they're nearby. Now when we look at the model for boron, we see that it's this flat, kind of triangular shaped molecule. And again, what are those bonds? What do those bonds actually mean? Those bonds are shared pairs of electrons. It means something very special. If we draw the molecule out the way we're used to, we see that it has, again, this flat structure, and this molecule is called borane. All right, we're going to continue the pattern. Hopefully we know how to draw carbon by this point. Carbon has 4 unpaired electrons. We're starting to see this pattern now, right? How many bonds can a carbon form? We already know that it's part of this 4-3-2-1-0 rule, but why does it make 4 bonds? Because those 4 electrons would like to have a buddy, right? That's the second thing we know about electrons. If we add hydrogens, this is going to be a pretty easy thing to imagine. We see now that we've achieved some of these noble gas configurations. We see that the hydrogens have all gotten what they wanted, right? They've gotten to be a helium configuration. And we see that the carbon, which was very far from the neon configuration, now from its point of view, it has the neon configuration. It has 4 electrons, 4 pairs of electrons, 8 electrons in total, and it has this noble gas configuration. And again, what are the noble gases? Noble gases are elements that don't form bonds with any other elements readily, like helium, neon, argon, krypton. These are the noble gases. So you're going to hear me talking about noble gas configuration quite a lot. Let's see what the result of these electron pairings is. We have our familiar methane molecule, right? 4 unpaired electrons has given us 4 bonds with those hydrogen atoms, giving us a molecule, right? Molecule is a set of atoms joined together. Covalent molecules have shared pairs of electrons. All right, and then our drawing of methane has this new significance for us, right? Because we understand what those lines actually mean, what those gray bonds really mean when we draw them or build them. All right, moving on to nitrogen. We can start to see that nitrogen, because of that 4-3-2-1-0 rule, right? We know that nitrogen will make 3 bonds, but now we start to see why, because we have 3 unpaired electrons. Those 3 unpaired electrons can pair up with hydrogen electrons, giving us noble gas configurations, right? From the point of view of the hydrogen, it feels like it's a helium now. From the point of view of the nitrogen, it feels like it's neon. And this is the force that's behind so many reactions in chemistry and why structures in chemistry are the way they are, right? This is the driving force behind it. Let's look at what we have when we look at the structure version of this. One cool thing that we're seeing for the first time is what's called a lone pair of electrons, right? Above the nitrogen, we see those 2 blue electrons. Those 2 electrons are actually not doing much of anything, right? They're not connecting atoms, but they are very important. So we're going to see the uses of those lone pair electrons later, but it's really important to think that they're there, realize that they're there, and also kind of get into the habit of drawing them. So when you draw an ammonia, one thing that you can remember is to draw those 2 dots above it, which signifies those 2 electrons, the lone pair of electrons. We're going to learn a lot more about those later. If you're not into them right now, don't worry, we can come back to it in later lessons, but it will be something important later. All right, moving on to oxygen. Again, if you are not quite have a foundation of why oxygen looks like this, check back lesson 3. But oxygen does have 2 lone electrons. Those electrons like to pair up. They have to pair up with something. Let's pair them up with some hydrogens. This is going to give us the structure of water, right? We've achieved noble gas configurations again. And when we see what the structure of water is, it makes total sense why we have 2 bonds now. And also, if we want to draw a very complete picture of water, we're going to indicate those 2 lone pair electrons around the oxygen. And again, that's going to be dealt with later on. Moving on to fluorine. Fluorine has a lot of lone pair electrons, doesn't it? It only has 1 unpaired electron, so we're only going to form 1 bond with a hydrogen. And noble gas configurations all around here, right? The fluorine was very close to the neon configuration to begin with, wasn't it? If we go back here, fluorine was only 1 electron away from neon. This is going to be really important for the properties of fluorine, actually. Fluorine is going to be what's called very electronegative. It's electron hungry. It would really like to be that neon configuration. It's so close, so it's going to really form bonds very readily to get that neon configuration, or even steal electrons readily to form that neon configuration, which we'll talk about in the ionic bonding chapter. All right, what does this look like? How does this translate to the models, right? We have 1 bond, that 1 pair of shared electrons. And there's our HF, hydrofluoric acid, or also called hydrogen fluoride. And we're going to see that if we draw it completely out, we're going to have 3 unpaired electrons around the fluorine. So to start to get into that habit of understanding that, if you also start to realize that, oh, what is that bond? What does that gray bond mean? That gray bond means 2 electrons. It's a shared pair of electrons though, right? So fluorine has 1 shared pair of electrons and 3 unshared pairs, or lone pairs of electrons, which equals 8. That's that octet rule coming in again. All right, and then moving on to neon, we can really see now why neon doesn't make any bonds, because we know that what's the driving force behind bond formation is the drive for electrons to pair up with other atoms, and we don't see that happening at all. There's no possibility for that in a neon. So neon is a noble gas. It's an element that doesn't bond with anything else, which is why we call it noble. And that's it. Nothing really too interesting with the neon here. These molecule diagrams that I have right here, these are so important. If you can rationalize why the atoms have the structure they do, and we can rationalize why the atoms have the molecules have the structure that they do, you're going to be able to go very, very far in chemistry, because so many molecules, and especially biomolecules, are based on these atoms. So if you look at your sheet, your practice sheet for this lesson, the emphasis is on drawing these bonded structures, drawing these shared pairs of electrons. Really, really work on this, because the rest of the course will be really falling into place for you if you get this. We're going to go a little bit more challenging now. We're going to go to the 3rd level of the periodic table and look at some bigger atoms and start to see that the trends repeat, right? Because the periodic table is, there's this idea of periodicity, that as we go from line to line of the periodic table, that the trends repeat. And we're going to see that happening for sulfur again. Now, sulfur is right below oxygen. Because of its location, there's no other way to do this than to think about having 2 lone electrons for sulfur. I think we built this in the last lesson as well. So now we can start to see why does sulfur have 2 bonds? Because it's a perfect match for 2 lonely hydrogens. This gives us not a neon configuration now, but an argon configuration, right? We're only 2 spots away from argon, so that's the noble gas that sulfur dreams of being, right? So now we're going to fade over to the bonded structure of hydrogen sulfide. We saw that because we have 2 sets of bonding electrons, therefore we have 2 bonds. And the molecule looks a lot like water, doesn't it? And that's because of the periodic trends, right? Because sulfur is in the same column as oxygen in the periodic table, we get a very, very similar chemistry. And again, we're drawing those outer electrons, those paired non-bonding electrons, as those 2 sets of dots around the sulfur. We're now going to start to build some larger molecules. We don't always have to have hydrogens forming bonds, right? Really, any molecule with unpaired electrons has the potential of pairing up with another molecule, another atom that has unpaired electrons. So here we have a fluorine, which we know has 1 unpaired electron. Other fluorines can also satisfy this octet rule, right? This drive to having 8 electrons in the outer orbitals. When this happens, both atoms, again, achieve a noble gas configuration. They both feel like they're neon atoms in this way. But really, what we have here is the formation of a molecule. This molecule we've seen before. This is F2. This is fluorine gas. And now we know what that bond is, right? Why only 1 bond? Same reason we had only 1 bond for HF. We have 1 bond for F2. That is fluorine gas. And look at all those unpaired electrons. All those non-bonded electrons around the fluorine. All right, now let's look at some oxygens. I'm going to draw these a little bit of a different way because we're going to start to expand on what our ideas of bonds are. We can see that I drew this oxygen atom kind of the same way. We still have 4 electrons in pairs, 2 electrons out of pairs, but I kind of shifted those electrons around a little bit, and you may start to understand why. Oxygen wants to make 2 bonds, right, because it has 2 unpaired electrons. What about another oxygen? Other oxygens have the same situation, right? They have 2 unpaired electrons. What if we could do something like that? Wouldn't that be interesting? This is a molecule that we know already. We do already see this noble gas configuration being satisfied, right? We do have an octet around each atom, just a little bit different than before. And if a bond is a shared pair of electrons, then what do we have here? We have 2 bonds, right? We have 2 shared pairs of electrons between these atoms. So therefore we have a double bond. And you guys have already built these with your model kits, so you're familiar with the concept of double bond. That's what a double bond means. A double bond is 4 electrons shared between 2 atoms. This is oxygen gas, of course. All right, moving on to nitrogen. I'm also drawing the nitrogen kind of the same but different, right? We know that there's a pair of electrons in the outer orbital and 3 unpaired electrons in the outer orbital. I'm drawing them kind of shifted a little bit because we're going to use them in a little bit of a different way, right? How many bonds does nitrogen make? We know from the first lesson how many bonds nitrogen makes. It wants to make 3 bonds. What if those 3 unpaired electrons were used by 3 other unpaired electrons? Wouldn't that be very convenient, right? Let's bring them together. Now we have 3 sets of shared electrons. So if a bond is a shared pair of electrons, a double bond is 2 sets of shared pairs of electrons. A triple bond is 3 pairs of shared electrons. So this is the triple bond. We've achieved the octet rule, right? From the perspective of each of those nitrogens, we have a neon configuration, and this is the triple bond, right? Each set of shared electrons is a bond. And of course, you've drawn this and you've made this in previous lessons. That's nitrogen gas. All right, moving on to another gas from lesson 1. This, of course, is a carbon atom. I've spaced the electrons out a little bit because I'm going to be using them a little bit differently. We know that carbon wants to make 4 bonds, but what if we could use, instead of those 4 unpaired electrons making 4 individual bonds, what if we could do something like this? Wouldn't this be interesting? Can you make some predictions about what's going to happen here? We know that oxygen, we saw, made double bonds before. So we may have a little hint there of what's going to happen. We're just using those unpaired electrons in a different way. How many bonds and what kind of bonds do we have here? Again, we do have 4 bonds altogether, right? Because carbon has to make 4 bonds. Each oxygen makes 2 bonds. We've achieved the octet for all the atoms involved. And we have this familiar structure, the carbon dioxide gas. That's what those double bonds mean, right? Each bond is a shared pair. So if a double bond exists, it's 2 shared pairs. And again, I'm emphasizing those lone pair electrons, which we will talk more about later. But we see that oxygens tend to have 2 sets of electron pairs around them that are not part of bonds. They're used for other things, as we'll see later. All right. One of the most famous kind of bonds in chemistry are the carbon-carbon bond. That's what we're going to see here. We can use carbons not just to bind hydrogens or oxygens, they can also bind with themselves. So this probably should start to make sense for us right now. If we have 2 carbons bonded together, we can fill out the rest of the positions with hydrogens. Octet rule for the carbons. We have what maybe you would call the duet rule, right? The duet rule for the hydrogens because they all got in the helium configuration. This is a very famous molecule called ethane. Ethane is a molecule very similar to ones that you've built before, and we get the bonding of what it is all about now. Let's extend the chain a little bit more. Let's now have 3 carbons combined. We can see where we're going here, right? We can have this almost infinite length and infinite variety in how carbons combine. We can just get longer and longer. This is propane. Propane like as in propane gas from your barbecue grill. This is what you're burning in your barbecue grill. I think we've talked about it briefly before. Let's extend our variety here. Let's have 2 carbons combined, 1 oxygen combined. Okay, this is the chain of the heavier atoms. We can then fill in with the lighter hydrogen atoms, fill in all the empty lone electrons. And this is the sort of the pattern that you're going to see throughout organic chemistry, that heavier atoms form kind of a chain or a backbone of a molecule, whereas the hydrogens kind of encrust it and sort of take in the positions on the periphery. That's something that you're going to get used to seeing a lot of. And this molecule you've built before. And just take a second to remind yourself what it could be. This is ethanol, right? The molecule that looks like a little doggy if you made it a model of it. And now we know, oh, actually the head of the doggy actually has some electron pairs on it. And later in the units when we start building with the model pieces that are the lone pairs, you'll see it actually looks even more like a dog when we build it that way. All right, and finally, we're going to build quite a long molecule now. We're going to start off with the oxygen, right? Oxygen, we see from its position on the periodic table, has 2 positions empty. That means it can form 2 bonds. Carbon has 4 positions that are empty. It can make 4 bonds. And then nitrogen has 3 positions that are empty on the way to neon configuration. So we need 3 bonds there. That's another way of looking at it. You can look at the periodic table just to directly see how many bonds you need, right? Wherever those white unfilled in boxes are, that's how you know how many bonds you need to make, at least for carbon on over. All right, let's use these unpaired electrons to form a bunch of bonds. The unpaired electrons that remain, they can't stay like this. Okay, this is a very unstable situation. You can't have atoms that are like this. So you have to connect something else to it. Hydrogen is the most common element in the universe, so this tends to be the element that gets connected when we have this situation. And now we've created an even longer chain with a whole bunch of different colors here. This is a cool molecule, and let's look at the structure of this one. This is ethanolamine. So it's ethanol with an amine on it. Amine is similar to ammonia, right? We've seen the ammonia, we've seen the alcohol, which is on the right side. In later lessons, we learn the functional groups. We learn how to name where these names come from. But yeah, that's ethanolamine. All right, so my suggestion here would be to go back over all these molecules that we've drawn out. And if you haven't been drawing them, make sure that your students are drawing out all these structures and all the different nomenclatures that you are seeing here, and then also build them as well, because the more you build, the concept really will sink in. For the homework for this unit, we have a molecule that we're going to use a lot in the next class, in the unit 5. Try to draw yourselves an ethylene in the style that we saw before with the circular orbitals. Try to figure out how you would draw this ethylene molecule, C2H4. And then there's also a bunch of simple molecules that you can continue to practice your literacy and how you connect molecules and draw them, and the proper number of bonds for each kind of atom. And this will all reinforce the concepts that we've been learning as we build to more and more complex things as we go. All right, well, thank you so much for joining for lesson 4. And things get very exciting in the next few lessons. So I'm looking forward to presenting the next lessons to you.